Hello again, everyone. Welcome to our discussion of section 5.6, where we will talk about applications of what we've learned so far about logarithmic functions and natural logarithmic functions. In addition to what we've already learned about solving logarithmic or natural logarithmic or exponential functions, in addition to those, we will learn about two more formulas. Together, we will be able to answer all the questions in this section. Again, this is because this is application type problems, so we will mostly, or actually mainly, deal with word problems. So it's basically applying all those things we've learned to solving word problems that can be written in terms of exponential functions or logarithmic functions. As usual, before we get into the details of this work, please let me remind you to skim through this section 5.6, spend maybe 45 minutes on this section, reading through it, just to get a feel for what is being discussed, the techniques that are being used, and to get a feel for the formulas that are being applied in general to solve these kinds of word problems. Then watch this video and attend the class and take detailed notes about the things that might be important to you or the questions you might have as we cover this topic. And the third step is review your lecture notes and go back to the textbook section and redo those problems you saw in the book without looking at those solutions, and come back to the video and revisit these problems that I go over without looking at the solutions I give. Preferably, even when you watch the video for the first time, you should pause the video and solve the problems before you see my solutions. That, number 3, is key. The key thing to learning everything we've discussed in this class, and it is the key in learning all the material in all quantitative classes. Number 4, please make sure that you complete the homework by the due date. And number 5, of course, please review the previous material. By now, I am sure if you had any doubts about whether reviewing previous material would be necessary in this course, by now I am sure you will 100% agree with me that reviewing previously covered material is indispensable to being able to solve problems in this course, because all of mathematics is cumulative in nature. So we cannot forget about the things we learned in the previous sections and even previous courses, mathematics courses. All right, so with the applications types problems, one of the things that is important for us to know is the concept of doubling time. Doubling time is the time it takes for any quantity to double itself. Now, we might be talking about money. So in that case, we are talking about the time it takes for an investment to double itself. Or we might be talking about some population where our objective is to find how long it takes for that population to double itself. Okay, that's the concept. One of the two formulas that I mentioned we need to learn in this section or apply them in this section is this one. The continuous compounding of interest or continuous growth. So the continuous nature of growth or compounding of interest will require us to apply this formula. The key word, of course, being continuous. A lot of times, well, let me remind you that not too long ago, we learned about the compound interest formula. Remember that? The compound interest formula was like this. Was some, well, I'll use the same notation that your book uses. Remember this formula? Remember this? That the future value or future quantity depended on the initial quantity times 1 plus some growth rate, some interest rate, annualized interest rate, divided by the compounding period. All of that raised to compounding period, compounding of interest period, times then t, which in that case was the number of years. Remember this formula? We did use this, right? Now, more specifically, this formula has this name. Periodic compound interest formula. So it's periodic depending on what the value of n was, right? N, as you recall, could be equal to 1, could be for annual compounding of interest, could be equal to 2 for semi-annual compounding of interest, or equal to 4 for quarterly, 12 for monthly, and 360 for daily compounding of interest. I am sure you remember us using this formula in one of the previous lessons. Now this one is not periodic interest or compounding of a quantity, it's continuous compounding of interest or continuous growth in some kind of quantity. I say this and I emphasize it with the word continuous boxed because over the years, every time I've taught this subject, my students always ask me, well, when do we know to use this for an investment, and when do we know to use this for the growth of an investment? I tell them, just look at the word, is the word continuous present? If it is present, then you have to use this. If the word continuous is not present, and instead you have monthly compounding of interest, or quarterly or semi-annually compounding of interest, then you would use this formula. So which formula we use depends on a careful read of the problem statement to see the clue to which formula is in the problem statement. Okay? So as far as definition of these variables, the P of t is future value of the population or an investment. P naught, this is P naught or P0, P naught is the initial population or investment. So given some initial investment or initial population, we can predict based on this model or equation the future value of an account or the future value of a population, the future population based on this formula, if the population or the investment is experiencing an exponential growth. Okay? So a continuous exponential growth, that is, a continuous exponential growth. So that is the prerequisite. And the problem statement must make that clear to us. Do these quantities have continuous exponential growth? If yes, we will use this formula. And then K is the rate at which the population is growing continuously, or the interest rate at which money is growing continuously. So if the problem is talking about some kind of investment, if they want us to use this formula, they should clarify and say that this interest rate, say 1.5%, is it continuous or is it quarterly? Is it monthly? If it's quarterly, monthly, or semi-annually, we will be using this formula. If the interest rate is continuous, then we will be using this formula. And of course, I'm sure you've made a note of, you've taken a note that the base of this this exponential function, the continuous exponential function, is e, right? So it's the natural exponential function. In other words, the natural exponential function, which we introduced a couple of lessons ago, is the continuous growth or decay function. Okay, and I say growth or decay because quantities can have exponential decay or decline rather than growth. Okay, if it's a continuous decay or decline, then we still use this formula. But in such cases, k would not be positive, as this is saying, because this is just talking about growth. This formula is just talking about growth. But if we had decay, that k would have been negative value. That's only the difference between growth and decay. And time, in this case, is in years. But the time can be changed. It can change. It can change to be daily, weekly, monthly, anything. But if that happens, then we will have to make sure that the units we use in the problem are consistent. So if some quantity is given to us on a weekly basis, and then we have another quantity given to us on a daily basis, then we have to make sure that those units are converted to the same unit before they are used in the formula. So weekly, for example, is supposed to be converted to daily. So for, say, 3 weeks, instead of day, we have to convert that to days to 21 days. Okay? These are the things that we have to keep an eye on as we solve problems. So that's one of the two formulas that we are introducing in this section. Another formula that we're learning about in this section is this one. Kt equals natural log of 2. So what does this formula represent? So exponential growth rate or doubling time, that would be t, or decay rate and half-life are related in this form. So the exponential growth or decay rate, that would be k. That's the definition of k given to us right there. The exponential growth or decay rate is called k in this formula, and the doubling time or half-life is called capital T, are related by this formula. Notice that in this formula can be used for both growth or decay, the doubling time or half-life. So if you have half-life, then you're dealing with decay, right? So this half-life is the opposite of the doubling time. We already said that the doubling time is the time it takes for a quantity to double itself. Whether it's population or money, it doesn't matter. The half-life, though, it's the time it takes for a quantity to halve itself, to become 1/2 of what it used to be. That's called the half-life. So whenever we have decay or decline, we're dealing with half-life. On the other side, whenever we have growth, we're dealing with doubling time. Okay? So growth rate leads to doubling time. Any growth rate has a doubling time. Any decay rate has a half-life. Okay? Those two are connected in that fashion. This is a very useful formula, as you will see in this section. Okay, so let's begin with this first problem. It says, under ideal conditions, and I strongly encourage you to please pause the video at this point and solve this problem on your own, and then come back to the video to compare your solution with mine. So I'm assuming you've done that, and now you're back. Under ideal conditions, a population of rabbits has an exponential growth rate of 11.7%. So this quantity, that's a growth rate, right? Growth rate means that is our K. in the formulas that we just saw. And it's an daily growth rate. Notice that? That's the unit, daily, per day. Consider an initial population of 100 rabbits. So in this formula that we just looked at, so K, we just determined that it's 11.7%, right? Then they say the initial population of rabbits is 100, so that's P naught. P naught is the initial population or investment. Okay? So therefore, let's assign variables to these quantities. So that is P naught. That was K, this is P naught. Okay? Find the exponential growth function for the population of rabbits. Well, the general exponential growth function is this one. So P of t equals P naught times e to kt power, right? K times t. So this is the general form. For this specific case, it'll be P of t equals 100, which is P naught, times e to 11.7% times t. We need to convert this to decimal. So 0.117 t. Okay? So that's all they want us to do for this section. Next, they'll say, what will the population be after 7 days? So we already established that the units of time were, or the growth rate was this much, 11.7% per day. So knowing that, then we can apply this 7, or we can replace t with 7 directly, right? Because t represents days in this case. Okay, and let me actually add that t is in days. And that makes it clear that growth rate is a daily growth rate, not monthly, not weekly, not annually. That's a daily growth rate. So t represents days. So what will the population be after 7 days? All we have to do is substitute for t with 7. So the population after 7 days is equal to 100 times e to 0.117 times 7, right? So how do we calculate this? Well, we have to observe order of operations. Remember that? When we calculated for the periodic compounding of interest, remember those examples? We had to follow the order of operations, calculate the inside of the parentheses. I'm talking about this formula. When we did examples like this, using this formula in the previous sections, we calculated the inside of the formula, inside of the parentheses first, then raised it to that power, and then lastly, we multiplied it by P naught. That's because the order of operations is that way. With this case, it's the same thing. We cannot multiply 100 by e first. We have to raise e to this exponent. Whatever the result, we multiply back by 100. So we have to observe the order of operations. Otherwise, we will get a totally wrong answer. So therefore, to follow the order of operations, and let me move this a little over so I can put my calculator here, like that. Okay, so we want to raise e to this power. So let's do that. There, I activated my e button, which is the natural exponential function button. In the parentheses, I'm going to multiply 0.117 times 7 before closing the parentheses. So 0.117 times 7 close parentheses, and enter. So that's the value we get. Actually, I mean, if I had to write this on a piece of paper, I would round this number because this is an exponential calculation in the middle of the calculations, right? In the middle of calculations, when you deal with exponential functions, you want to keep at least 4 decimal places, the numbers up to 4 decimal places. That would mean I would have to keep all the way until 2, at least. If you round too much too early, if you use 2.3, your final answer, because you're dealing with exponential functions, your final answer will be off by a large margin. So with exponential functions, we want to keep at least 4 decimal places. So, but in this case, that's an easy calculation. I'm not going to even round that. It's right in front of me. I'm going to multiply this quantity by 100. Okay, we can do that. So let's do that. Times 100. So there we have it. So the population of the rabbits, it would be 226.8, but let me round that. Roughly, that would be 227 rabbits, right? Okay. Rabbits. Okay, like that. So then they say, what about after 2 weeks? Okay, so this was rabbits after 7 days. Okay, so now we need to make this calculation again for 2 weeks. But weeks is a different unit than the t, which is in days. So what do we have to do? We have to convert this unit to the unit used in the formula. Why? Because this growth rate is daily growth rate. So we need to convert this unit to whatever the unit of the growth rate is. And the growth rate is has a daily unit per day. So this weekly must be converted to daily units. Okay, so we have 2 weeks is equal to, of course, 14 days. Okay. Now we have a number that is in the units of the growth rate. So let's plug in. The population of rabbits after 14 days is equal to 100 e to 0.117 times 14. I hope that this answer matched whatever answer you got when you solved this on your own. And I hope we agree on this one too. Okay, so once again, let's make sure that we follow the order of operations. This e to that power, so there, I got my natural exponential function activated. Then let's multiply inside the parentheses there. Let's multiply 0.117 times 14. And enter. So that's the quantity up to this point. Now, we don't even have to write this down. We can save time by multiplying what we have by 100. Okay, so let's do that. Times 100. There we have that. So 514.5 or roughly 515 rabbits after 2 weeks. Okay. Part C, it's asking us to find the doubling time. So now we can make use of this formula, right? The doubling time, T, remember, this formula can be used for growth or decay. If we have a half-life, we can use it for declining or decreasing quantities or decaying quantities. If we have a growing situation, like in this case with the rabbits, we use that in conjunction with doubling time. So kt equals natural log of 2. Let's make use of that formula. So we know that kt equals natural log of 2. We have this formula, right? So in this formula, k is equal to 0.117, right? 11.7%, which is that. That's the growth rate. That's k. So let's plug it in, and t is the doubling time. So plugging in, we have 0.117 times t equals natural log of 2. So t is equal to, right? We're solving for t. So we need to isolate t. Is t isolated? No, it's got a 0.117 next to it. So what do? We divide both sides by 0.117 to get rid of that and to isolate t. Okay, so therefore we have t equals natural log of 2 divided by 0.117. Okay, so we need to, this is a word problem, so we need to calculate the value of t. And let's do that here. Okay, so natural log of 2 divided by that quantity, 0.117. Okay, 5.92. So 5.92, or roughly, we can just, so if that's the doubling time, we can roughly say roughly 6 days, right? In other words, given this kind of growth rate for the rabbits, we expect their population to double every 6 days. Oops, let me make sure that it's on the screen like that. Okay, that's the interpretation of that quantity. All right, I hope these answers match the one that you have. Next, we will look at this situation where we're being asked to compute the missing values in the following table. So this is the country name, and there's some kind of a growth rate. We are not told what is it that they are talking about. Are they talking about population? Are they talking about, let's see, say air pollution? What are they talking about here? We're not told anything about that. So it's okay. We still use the growth rate, and doubling time. These two quantities are related with this formula. They are related using this formula, right? Kt equals natural log of 2. Okay, so I highly encourage you to please take the time to complete this table before you see me work this out. Okay. So for growth rate, we're looking for t given we have doubling times 77 years, right? So k times 77 equals natural log of 2. And therefore, k needs to be isolated, right? So we need to divide both sides by 77. Natural log of 2 divided by 77. So k is equal to, let's use our calculator, natural log of 2 divided by 77. So the growth rate is that, and we can convert this to percentage, right? So 0.009 or 0.9%. Okay, that's the growth rate. So multiply that by 100, you get the percentage form from the decimal form. Okay, so here, once again, we have to calculate the growth rate for Bolivia. So we have 42.5. Again, we would replace in that equation right here. So we have k times 42.5 years equals natural log of 2. We're solving for k, so we need to isolate k. To isolate k, we need to get rid of this 42.5. So divide both sides by 42.5, and we get k equals natural log of 2 divided by 42.5. So k is equal to, let's bring back the calculator. Right? So we have natural log of 2 divided by 42.5. We have 0.0163 or 1.63%. That's the k. Okay. Further down below, we've got the India. This time, this is k. The k is being given to us. This is k. So k, let's convert that to decimal form. So k would be equal to 0.0128. And let's plug it into the calculator, the formula. So we have 0.0128 times t equals natural log of 2. So t is equal to natural log of 2 divided by 0.0128. So natural log of 2 divided by 0.0128. What do we get? We get 54.15. So let's round that to 54.2 years, right? 54.2 years. I should have put all of this here. Sorry, guys. So this belongs here. This belongs here in this square. But all of this calculation should have been here. So this is where I should have written 54.2 years. Sorry about that. It should be, that number belongs in that square. Okay. So this time I won't make that mistake though. So this is 0.39%. First, this is our k. Let's convert this to decimal value, 0.0039. Then to calculate t, I'm going to come over to this square and plug in. So 0.0039 times t equals natural log of 2. So to solve for t, we need to isolate t. Is it isolated? No, we've got this 0.0039 next to it. So what do we have to do? Divide both sides by 0.0039. Like that. And then, of course, T will be natural log of 2 divided by 0.0039. So T would be equal to, let's bring the calculator over, like that. So we have natural log of 2 divided by 0.0039. So 177.7 years. Okay. 177.7 years. And that's for Hong Kong. But like I say, we don't know what they're talking about. Is this population? Is this pollution? Air pollution? What is this talking about? Okay, so that's that. Here, in this example, again, please pause the video, spend 10-15 minutes on this, write down your best solution, given everything that you know, including the formulas that we've learned in this section, and then come back to the video. Okay? All right, I'm assuming you've done that, and now you're back. So this problem is playing a trick. It's playing a trick because it introduces these percentages which might make one think that it's talking about the growth rate, right? The revenue from ebook sales accounted for only 0.5% of US publishing sales in 2006. This percentage grew to this much, 22.6% in 2012. Find the value of growth rate and write the function. So once you get to this point, find the value of growth rate, you say to yourself, well, I thought these were the growth rate. But if I'm looking for growth rate, what is it that these are then? So clearly, 0.5% and 22.6% are not the growth rate, are not K, because K is being asked about. So what are these then? That's the thing. Because most people might get confused because these are percentages, and in the formulas we've learned, only K is in percentage, but that's not always the case. So you can, in this case, you can treat this 0.5% as P naught, and this 22.6% as P after, and this was in 2016 and this is in 2012, so this is at P6, so 6 years. So this quantity is the growth, the percentage that grew to this much. The revenue, that's talking about the revenue from ebook sales, grew to this much. So this is the quantity that it's grown to after 6 years, from 2006 to 2012. The initial revenue from ebook sales was 0.5% of the total US publishing sales. Okay, so in 2006, 0.5% of all things that were published in the US were sold as ebook. In 2012, that grew to 22.6% of all US publishing sales. So out of the total things that were published and sold in 2012, 22.6% of them were sold as ebooks. Okay? All right. So given that, they want us to calculate K. Well, so we have this formula, right? Quantity T, quantity after time T, PT. So that quantity can be money, can be sales, revenue in this case, can be population, can be anything. So we are given this as 22.6%, and it was 0.5% in 2006. So in this case, P naught is 0.5%, and please remember we need to convert that to decimal form. And then K is what we're asking about, and T is, it's from 2006 to 2012 that this happened, so T is 6 years. So we have everything here we need except K. We can solve for K, right? K in this case is a variable in the exponent, and we are well versed in using techniques to solve for variables that appear in the exponent, right? We've done plenty of that, especially in the previous video or the previous lesson. So, all right, so let's write that down. The formula to apply is this: the revenue after 6 years equals the initial revenue times E to power K times T, right? So we know that T should be 6 years. So by the way, this is, well, I should have, it's okay, let me do this in steps. I don't want to make a mess out of this, but this is K times 6 or 6K, right? T is 6 from 2006 to 2012. So 6 times K is 6K. Now let's replace for these two quantities. The revenue after 6 years from sales of ebooks was 22.6%, right? So we need to convert that to decimal form. I think the screen is a little bit fuzzy. Let me try to focus it. I just noticed it. Okay, this is sharp. This is sharper then. So this should be 0.226 equals, let's convert that 0.5% to decimal form. That'll be 0.005, right? Just divided by 100. Okay? And then we have E to 6K. Let me use my scratch paper here. I'm not sure if you're comfortable with converting decimal to percentage and percentage to decimal, but just let's go over it very quickly. If you have 1.2% and you want to convert this to decimal, right? Well, let's say on this side we have percentages, and on this side, let me move this over a little bit. And on this side, we have decimals, values, right? Decimal values. So if you want to convert from percentage to decimal, you must divide this by 100. So then you get 0.012. You divide this by 100, you get the percentage, you get the decimal. Now, if you are given something in decimal value, let's say 48.6, let's say that's the decimal version. To convert this to percentage, you would have to multiply this by 100. So if you want to convert this to percentages, so this would be let's see, for decimal values, let's see, so this would be, well, it depends if this is something, yeah, if this is a growth rate, then this would be 4,860%. If this is times, if you want to convert this to percentage, you would multiply this by 100 to get the percentage form. Going back, you would have to divide this by 100 to get to that point. Suppose you have, well, let me write that here or here. Suppose we have 0.386 0.8%, right? So how would we convert this to decimal form? So we would divide this by 100, and we get 0.00368, okay? To convert this to percentage, you would multiply this by 100. Do you see the relationship? So suppose I have a decimal value, say 1.8, okay? How would I convert that to percentage? I would multiply this by 100. So 180%, okay? Multiply, so let me write that on here. When you're going from decimal to percentage, multiply by 100. When you go from percentage to decimal, divide by 100. Again, multiply by 100 and divide by 100. To go from percentage to decimal, divide by 100. To go from decimal to percentage, multiply by 100, and so on and so forth. Okay? I hope this is clear. So if you have 2, let's say 2 here for decimal value, that would be 200%. Right? So this is, again, you would multiply by 100 if you want to go from this form to percentage form. All right, so this is a quick mention of that topic. All right, in this case, that's what we did. We divided by 100 to find the decimal for each percentage. Okay, now our objective is to get to k, right? Which means if we're solving for k, we need to isolate k by itself. Look how many things are preventing k from being isolated. We've got, first of all, we've got the 0.005, then we've got this base e, then we've got the 6. The techniques to getting rid of each of these is going to be different. So how do we get rid of the 0.005 first? Well, we divide both sides by 0.005. Right? So on the left, let me calculate that. On the left, what do we have? We have 0.226 divided by 0.005. We have 45.2. Okay, so 45.2 equals, on that line, on that side, these two cancel out. We end up with e to 6k power. Well, k is caught up. It's caught up in a group. That group is the exponent of the natural exponential function, e. Okay? How do we ungroup it from being an exponent? We've learned a very useful technique in this section, right? Or in this chapter, chapter 5. Okay? Take the either log or natural log of both sides. That'll help bring this 6k down, and then we can separate the 6 from it. As long as they're up there as an exponent, they're grouped. So would you use log of both sides or natural log? If you said natural log, that's absolutely correct. It's better. It's not incorrect to use log. You can take the log of both sides. But taking the natural log of both sides, because this base is e, makes the solution easier. That's all. So natural log of 45.2 is equal to natural log of e to 6k power. Okay, so now on the left, what do we have? Let's calculate it. Natural log of 45.2, we're going to have to round. I have quite a bit. Natural log of 45.2 is that, right? So I'm going to keep all the way until 7. Okay? If you don't want to do that, keep at least round this 0 to 1. Let's do that. Let's round this 0 to 1 actually. 3.81 1. Okay? So 3.8111. Okay? So we kept 4 decimal places. Equals, now this 6k, we learned about properties of natural log and logarithmic functions last time, right? So we can make good use of those one of those properties. That 6k comes in front. So 6k times natural log of e. But another property we learned about in the last class or last video was that natural log of e is equal to 1, right? So we have 3.811 equals 6k times 1, 6k. Look how far we've come in isolating k, right? Look how it was, where it was, now look where it is. So is it completely isolated? No. It's got a 6 next to it. We got to get rid of it. How? Divide both sides by 6. So on that side we have k, on this side we have 3.811 divided by 6. So finally, let's calculate that. We have 3.8111 divided by 6. So 0.635. I'm going to round that to that, 0.635. But this is the growth rate, so and this is decimal form. So I'm going to multiply this by 100, right? Just like we talked about here. If you're going from decimal value to percentage, you got to multiply by 100. Remember this slide? So multiply this by 100, we get 63.5% growth rate. Okay. So it's a huge growth rate, isn't it? It's a huge jump in only 6 years. But I'm sure you know that the incentive to buy the ebook is not that most people prefer to read books or published material on a screen, but it's that publishers make it significantly less expensive for us to buy published material as ebook rather than purchasing it in hard copy form, right? So the cost and of course the convenience of that is a huge difference, because with ebook you don't have to go to a bookstore, you don't have to wait for it to arrive in the mail if you order it from online as a hard copy. So it's immediate, so it's more convenient that way. So the cost and the convenience have contributed significantly to that huge jump in sales of ebooks. Okay, so next problem. Again, please, at this time, it would be a good idea to please pause the video, write down your own solution for this. There is an example in your book. So if you took my advice and read the book, this section 5.6, before you watch this video, I'm sure you would have seen that one example that is very, very similar to this, and it comes at the very end of the section 5.6. Okay? Then this would have been an easy problem for you to solve. Okay, but in any case, if you haven't read that example, you're welcome to pause the video, take a look at the example in the book, and use that example to solve this one. This is not all like that, but it's very, very similar. I'd say they're 70% similar. Okay? All right. So I'm assuming you've done that, and you now have your own solution. It says, in February 2006, in the Valley of the Kings in Egypt, a team of archaeologists uncovered the first tomb since King Tut's tomb was found in 1922. Okay, so the tomb contained 5 wooden sarcophages, and sarcophagi. So that's those sarcophages or sarcophagi. That's a plural. Are the stone tombs where the ancient Egyptians used to store the royals after their death, or their mummies actually. So these are stone coffins actually, not tombs. Sorry, stone coffins are sarcophagi that contain mummies. The archaeologists believe that the mummies are from the 18th dynasty, about 1300 to, that's important, 1300 to 3500 years ago. Knowing that the radioactive element carbon-14 has a half-life of 5,750 years. What does that mean? That means if you suppose you leave 1 gram of, suppose there was 1 gram of carbon-14 5,750 years ago somewhere, right? That quantity now would be half a gram, because after every 5,750 years, the carbon-14 halves itself. It has a half-life of 5,750. Okay, so it's from that radioactive element, the 1 gram that was there 5,750 years ago, now there would be just half a gram, half of that amount. So that's a half-life. That's what we mean by that. Okay, determine the amount of carbon-14 that the mummies have lost. Well, this is okay, but they're approximating that the archaeologists believe that the mummies are from this dynasty about 3,300 to 35 years ago. Okay? So let's first find the decay rate, because we have the half-life, but the decay rate, in order for us to find the radioactive amount that the mummies have lost, we need to find out the growth rate, the decay rate first. So first, let us find the decay rate. I say decay or declining rate because it's a half-life, right? Doubling time would suggest growing quantity, a growth in quantity. But half-life suggests a decay rate or declining trend in the quantity. So let's find the decay rate K first, okay? But we have a formula for that. Given the half-life, we have this formula, right? We have the half-life in this case, half-life, not the doubling time, because this is a decaying quantity. Decay is related to half-life, right? The half-life is 5,700, which is T, is 5,750 years. So T is 5,750 years. K is question mark. So we can use, using KT equals natural log of 2, then we have K times 5,750 equals natural log of 2. So then K, we're solving for K, so K needs to be isolated. Is it isolated? No, it's got this 5,750 next to it. So we got to get rid of it. How? Divide both sides by 5,750. So it's equal to natural log of 2 divided by 5,750, which is, K is, let's calculate that. Okay, so we have natural log of 2 divided by 5,750. Okay, So that is the 0.00012. Oops, let me bring this on the screen. So I want to keep, let's see, I want to keep at least up to 5. So 1, 2, 0, 5. I'm going to stop there. Okay. So that's the K. Then they don't tell us how much radioactive carbon-14 must have been there these many years ago, right? 3,300 or 3,500 years ago. But we can guess, suppose if we had a gram of that back then how much of it was lost, okay? So we're looking for P of T in both of these cases. So this is, let's see, so I guess in my worksheet, see here, I don't talk about the fact, and I should add that. So in here, let me add something to this. This is where K is greater than 0 for growth. And I should modify my worksheet so it has this. And K is less than 0 for decay, or for declining quantity. K must be negative. And my worksheet is missing that, but now I've added it, and when I post this on Canvas, you're going to have this. So that's important because this K that we got, when we place it in the formula, in this formula, it should be minus. So we have, let's suppose that we begin with 1 gram, right? Because it's all a ratio. So, so let's see. So we have P, this is the formula that we're using. P of T equals P naught times E to K times T. And T, we have 3,300 to 3,500, right? So let's calculate for either case. And then, so if we take this to be initial quantity of carbon-14 that many years ago, let's say if it was 1 gram, right? So this much of it, so it would be reduced to this much. So let's assume that we take that to be, let's say, 1 gram, right? Assume P naught equals 1 gram. Because in the end, it's the ratio that matters, okay? So then P of T for when T is equal to 3,300 years ago, right? This is, let me highlight that. We've been given two years here, 3,300 to 3,500 years ago. I think I can fit all of that on this, in this here, in this space. So when T is equal to 3,300, then what do we get? We get the 3,300 equals, the P naught is 1 gram, so it's just 1, it drops out. And then E is E. K we just found out, but this will be minus K. This is what I was saying earlier, that my worksheet was missing that piece. K is less than 0, or it's negative number when we're talking about decay, but it's positive or greater than 0 when we're talking about growth. I should have made that clear on the front page. So here, that should be minus KT. Okay, that's my point. So minus K, which is that in decimal form, already converted in decimal form, minus 0.00012, 0.001205 times 3,300 years. Okay? So that's for this many years. Okay, so let's calculate this. It'll be, so this is how much it would remain, right? So then we have to subtract this from 1. Why? Because they say how much of the carbon-14 the mummies have lost. Okay? How much they lost, not how much is remaining. This formula is going to tell us how much is remaining. Let me make that clear. This is remaining carbon-14. Okay, so we need to subtract that from 1 gram, whatever that is. Okay, let's see. So now all we have to do is calculate this quantity. So E, so E, natural exponential function, to this exponent, minus 0.00001205 times 3,300, and remember to close the parentheses. So enter. It's so all of that is 0.67. Let me keep up to, let me round this 8 to 9. 0.6719. Okay, so this, if we started with 1 gram, started with P naught, we started with 1 gram, so this much is left. This is remaining. Remaining carbon-14. So how much was lost? Oops, let me move this up. So 1 minus 0.6719, right? Let's do that. 1 minus 0.6719. That much was lost. About 0.33 grams was lost. About. So about 0.33 grams lost after 3,300 years. After 3,300 years. Okay, so let's do the same thing for when T is 3,500 years, because they tell us between that much and that much. So if the mummies, the mummy had died, or the individual had died and was mummied 3,300 years ago, that much must have been lost. So we would expect this to be more if the dummy or the mummy had died 3,500 years ago, right? We would expect this to be less. So let's see. So let me use my black ink in this case. So P of T, again, assume P naught is equal to 1 gram. So once again, we assume that's 1, so it drops out. Then E to minus the same thing, the K is the same thing, 0.000125. This time, instead of 3,300, we're going to use 3,500. Okay, so let's calculate that. Oops, I have to come back to the screen. I keep forgetting. Okay, that's all right. Now that's on the screen. Okay, that's better. So E, the natural exponential function, to this power minus 0.000125 times 3500, and then close the parentheses and enter, and we get that. So let me use 0.6559. I'm going to round that 8 to 9. So 0.6559. Okay? All right. So this is, again, remaining. This is remaining carbon-14. We don't want that. We want the amount of carbon-14 that the mummies have lost. Okay? So we need to subtract this from 1 gram. This is how many grams is left. We need to subtract it from 1 gram. So 1 minus 0.6559 equals let's see, 1 minus 0.6559, 0.34 grams. So this would be 0.3 grams lost, right? Which makes sense. More grams were lost because this was a longer period. It was 3,500 years as opposed to 3,300 years ago. Okay. In the next problem, it says, suppose that $10,000 is invested at an interest rate of 5.4% per year. So notice in this case, the percentage or the interest rate is per year, right? The unit is year. Compounded continuously. That's what I was talking to you about. So people are asking me, how do we know we should use that formula? Compounded continuously. With carbon-14, the word continuously was of course missing, but in the natural world, all decay or growth rate happens in that fashion, continuously. Rarely you might find, I don't know, linear. It might be also linear. Suppose a long time ago I was looking at, in graduate school, I was looking at the rise in the temperature on Earth, the average temperature around the globe, and up to 1990, of course, I think, if I remember correctly, up to, and the data goes back, it goes back to, I think, 1930s or something like that. But from that point to about 1990, 1991, the rise in the temperature was linear, not exponential growth in the rise of the temperature, or exponential increase in the temperature. But I think since then, I think what I noticed after 1991, the rise in temperature on the planet had taken an exponential growth rate. Okay, but in the natural world, especially for carbon-14, the decay rate is exponential. So even though continuous exponential, a continuous exponential. So even if they don't tell us to use that formula, we know we should use it, okay? Because it's the nature of radioactive carbon material decaying over time. It's always continuous decay, okay? But this is talking about money, and monetary instruments can be can have periodic compounding of interest or continuous compounding of interest. So they have to tell us, and in this case, they do tell us that it's in fact continuous compounding of interest. All right, so as we read this, we should be careful or mindful of what these quantities represent. And again, I hope that you've already downloaded this, or even now, if you pause this video and solve this on your own, that'll be great before you look at my solution. But then this, if $10,000 was invested, then this quantity is our initial investment, right, or P naught. The initial investment, P naught, is invested at an interest rate of 5.4%. So this is K, which we need to convert to decimal form. Remember? How do we convert a quantity to decimal form, from percentage to decimal? We divide by 100, right, to go in that direction. Right? So we divide this by 100, we get 0.054. Compounded continuously, and of course this statement means that we need to use this formula. P of t equals P naught times e to k times t power. Okay? Find the exponential function that describes the amount in the account after time t in years. So t is in years, right? We have to use t. All right? So we're almost there, right there. So P of t equals, the initial investment was 10,000. Let's substitute that here, 10,000 times e to k times t. So k is that 0.054 t. Okay, that's all they're asking. They're asking for the exponential function. They're not asking us to solve for any variable. They say just find the exponential function. So this is it. This answers this piece. Okay, then part B says, what is the balance in the account after 1 year and then after 5 years? So basically, and the units of t is already in years. So they're asking us to find this quantity, P of t, the future value of investment after 1 year, after 5 years. Okay, let's do that. So t equals 1, then P at 1, after 1 year, it's 10,000 times e to 0.054 times 1, right? T is 1. Okay, so then we have to observe the order of operations. Please remember that. That means we need to raise, let me move this over a little bit, like that. That means we need to raise this e to this 0.054 before multiplying it by 10,000. Okay, so let me activate the exponential function. There it is. Raise it to 0.054 times 1 is itself, close the parentheses, and that. So I have that in front of me. I'm not going to round it. It's easier if I just multiply that back by 10,000, right? Times 10,000. What do we get? We get that much. $10,554.85. Let's write that down. So $10,554.85. That. I hope this matches the answer you got. Let's do the same thing for T 5 years. How much is in the account after 5 years? Right? Just doing that. 0.54 times 5, right? times 5. Okay, so again, we have to observe the order of operations. Let's raise the exponential function to that quantity. Whatever we get, we multiply it back by 10,000. So 0.054 times 5, close the parentheses. There's the quantity, multiplied back by 10,000. And there we have it. We have 13,099.64. Okay. I hope this matches what you have. Okay. So then they tell us what is the doubling time? Right? Do you know how to go about answering that? If not, pause the video, think about it. It'll take us a couple of minutes to answer this one. Right? Because we know that the doubling time and the growth rate are connected using this formula. We know that. So we know K is 0.054. Times T equals natural log of 2. So T, which is the doubling time, equals natural log of 2 divided by 0.054. Okay, so the doubling time is simply equal to, let's see, where should I put this? Like that. So natural log of 2 divided by 0.054. So there we have it. The doubling time is 12.8 years. It's very fast, isn't it? And this is roughly that, so we're rounding this. So 12.8 years. Okay. This is quite fast. So in 12.8 years, this $10,000 is going to reach to 20,000. That's quite fast. But it is fast because the growth rate is continuous. That means even less than a second, this investment is growing. Okay, like that. Next, we will look at the oil consumption per day in China. Okay, so suppose we have this scenario. And please, if you haven't done so already, please pause the video. Pause the video and solve this problem, and then unpause the video to see what I have done. It says in 1980, China consumed 1.885 million barrels of oil per day. So when they refer us to that time, it's quite likely that this is, and in here they clarify it, but 1.85 million barrels, that is the initial quantity. Initial consumption. Okay, that's that per day. By 2012, that's 32 years later, that consumption had grown to this much, right? So this is P of T. That's the amount after 32 years, the daily consumption of oil in China. Okay? Assuming that the consumption of oil, C naught, C naught, they call it C naught, so let me call that also C naught. So I'm going to correct that with my thick pen here. I'm going to say C naught. Okay? I want to be consistent with that. C naught. C naught. Okay? Assuming that the consumption of oil in China has grown exponentially, okay, and that's continuous exponentially. Find the value of daily oil consumption growth rate K and determine the exponential growth function. Okay, so we went this quantity, so this is the clue for us that right here has grown exponentially because of this clue, and this has to be continuous, right? It's not quarterly or semi-annually. This is not money we're talking about. This is consumption of oil, so it's continuous. So because of that clue that I've highlighted, we know we have to use this formula. Okay. Then they say, find the value of daily oil consumption growth rate. So K is what we're finding. Find growth rate K. Okay. And determine the exponential growth function, assuming that this is that. So they're saying find K and then set up the consumption function, exponential consumption function for daily, for oil in China, for oil that is consumed daily in China. Okay, they say find K and then set up the function. That's what they're asking. And T is the number after 1980. So from 1980 to 2012, that's 32 years, right? So from 1980 to 2012, 32 years have passed. Okay? All right, so T is 32, P naught it's 1.85, and that's units is millions. And then, and this PT is 10.28 million. Okay, so let's substitute and solve for K. 10.28 million equals 1.85 times E to K times 32, or 32K, right? Okay, so we're solving for K. That means we need to isolate K. Look how many things are on our way of isolating K. So the first thing is this 1.85, right? How do we get rid of it? Divide both sides by 1.85. That's the technique to use there. On the left, what do we get? Let's look at it in our calculator here. So 10.28 divided by 1.85, so we have that quantity, right? So on the left, because this is an exponential function, I'm going to keep all the way to that 7. I'm going to round that 7 to 8. So 5.5568 equals, on the right, those two cancel each other out. Instead, we get E to 32K power. Now what do? K is in the exponent, and base is E. Would you take the log of both sides or natural log of both sides? Well, the base is E, so the easier way would be take the natural log of both sides, right? So natural log of 5.5568 equals natural log of E to 32K. On the left, what do we have? Let's calculate it. On the left, we have natural log of 5.5568, which is 1.715. So I'll keep all the way to 5, 1.715. 1.715 equals, on the right, we have 32K. Remember that exponent comes in front, multiplies itself by natural log of E. We have a property that says natural log of E is equal to 1. Okay, 1 times that is itself. So we end up with 1.715 equals 32k. So we're solving for k. This 32 is preventing us from isolating k, so all we have to do is divide both sides by 32. So on the right, we just have k. On this side, let's divide 1 point that by 32. I already have the number up, so I'm not going to retype it. Divided by, not to mention that that was a more exact or more precise number. Divide by 32, we get 0.05. So I'm going to keep all the way to 5, and I'm going to round the 5 to 6. Okay, so 0.0536. Okay, so that's the growth rate. So we've answered part of the question, and if we need to convert this to percentage, what do? If we have a decimal form, well, this one, that one is going from percentage to decimal. If we have the decimal form and we want to convert to percentage, what do? Multiply by 100, right? So we can say either that or k, multiply this by 100, you get 5.36%. Right. So either this or that. So then they say determine the exponential growth function. So all we have to do is just write down the function. That's all. That is equal to, oops, I'm off the screen. Sorry about that. So given this growth rate, we have the initial quantity doesn't change, right? This was the daily consumption of oil in China in 1980. So that's our point of reference, 1980. So we keep this as it is, then times E to this growth rate, 0.0536 times T. Okay, so that is the exponential function for daily consumption of oil in China over the years. Okay, so now this one, the next part is saying estimate the consumption of oil. And by the way, I should add here, the T is years after 1980. So that's what T represents. So if you said, what's the daily consumption of oil in China in 1985, then T would be 5. If you said, what's the daily consumption of oil in China in 1990, T would be 10. Now this is saying estimate the consumption of oil in 2005. So that's how many years? 25 years, right? So because of that, T is equal to 25 years. Okay? Because the reference here is that, 1980. All right? So in this formula, simply let's plug in for T with 25 and answer this question. So T is 25 equals 1.85 times E to 0.0536 times 25. Okay, so we have to observe order of operations. Remember that, please. Which means we need to first calculate E, the exponential function, to this power. So let's do that. Okay, like that. So we have the exponential function, 0.0536 times 25. It's that. I'm not going to even write it down. It's ready for me to multiply by 1.85, right? Times 1.85, and it's let's round that to 7.1 million barrels per day. Okay? Per day. Okay? Like that. All right. All right, so now it says, oh, this is continuation of that. It has a part C and D. I thought this was new problem. Okay, what is the doubling time for the consumption of oil in China? Well, we have that. If you haven't answered these two parts, please go ahead and answer it and then come back to the video. I'm assuming you've done that. And if you've been doing that, I thank you. And then what is the doubling time? So we have this nice formula, KT equals natural log of 2. We already know what K is, right? K was 0.0. K was 0.0536. All right? That's K. So 0.0536 times T equals natural log of 2. So T, which is the doubling time, right? They're asking for the doubling time. That's T. Doubling time is natural log of 2 divided by this, right? Because we want to isolate T. 0.0536. Okay, that is equal to, let's find out. Natural log of 2 divided by 0.0536. So 12.9 years. Roughly 12.9 years. Okay. So that means every roughly 13 years, the daily consumption of oil in China will double itself. Okay. All right, so part D says, after how long will the consumption of oil in China be 13 million barrels per day, assuming that there is no change in the growth rate? Well, we're almost there, but because of that, let's calculate this. I didn't realize, I should change that actually. I should change this worksheet because of two things, right? Because we're almost there, so no, actually that's different. But so because I need to add this for when this formula is applied to decay, K must be some negative number. So K is less than 0. So I need to add that. But this is saying, so in this case, they're asking when P naught, PT, when P of T is 13 million, how long will it take? Because we know that the initial, in 1980, the oil consumption was how much? 1.85, right? 1.85 in 1980. They're saying given that, oops, let me bring this back to the screen. They're saying given the fact that in 1980, China was consuming this much oil, million barrels per day in 1980, by when, how long will the after how long will the consumption of oil in China be 13 million barrels? Okay, so this is a different question than that. So 1.8 million barrels per day. I want to make that clear. Okay, so that means in this equation that we have, which is that, in this equation, P of T is 13 million, and the units are already in millions, so I'm just going to say 13 equals 1.85, which was the initial quantity in 1980. That's our reference here, right? This is our reference year. Everything is compared to that year. 1.85 times E to 0.0536 T. So T is the unknown. How long it'll take, how many years it'll take for this initial quantity, 1.85 million barrels per day, to reach 13 million barrels per day. Okay, how we're wondering about that. So T is the question mark, which means we need to isolate T. Look how much work we have ahead of us before we are able to isolate T. So the first thing is get rid of this 1.85, right? How do we get rid of that? What's the technique? We divide both sides by 1.85, right? Like that. So what do we have on the left side? The 13 divided by 1.85. Okay, 13 divided by 1.85, it's 7 point something, right? I'm going to keep all the way to that 2. I'm going to round that 2 to 3. That 2, I'm going to round that to 3. So 7.02703. Again, because we're dealing with exponential functions here, you don't want to round this to 7.0. Your final answer will be off by a large amount. So you want to keep at least 4 decimal places, if not 5. In this case, I've kept 5. Okay, so that. And then, so on the right, the 1.85, that's been canceled. So now we have E to 0.0536 T, right? Okay, T, we need to isolate it, but it's part of the exponent, and the base is E. Do you know the technique we can use to bring the T down? The easiest technique? You can take the log of both sides, but the base is E, so it's easier if you take the natural log of both sides, right? Let's do that. So natural log of 7.02703 equals natural log of E to 0.0536 T. Okay. Let's find out what that quantity is. Okay. So, natural log of 7.02703, 1.9497. I'm going to round that 7 to 8. So 1.9498. 8 equals, on that side we have 0.0536 T times natural log of E. Well, last time we learned that natural log of E is 1, right? That's why whenever the base is E, it's easier if you take the natural log of both sides because of this. Then on the left we have this. So what do we have for T then? We have one more tiny step to take to isolate T, right? We have this quantity to get rid of. So divide both sides by that quantity. We have, so 1.9498 divided by 0.0536. So what we're doing is simply divide both sides by that. That's what we're doing. Okay? All right, so let's figure out what that number is. So we have 1.9498 divided by 0.0536. 36.4. Let's round that 3 to 4. Almost 36.4 years. So after 36.4 years from 1980, the oil consumption in China, the daily oil consumption in China would have doubled. And we've already passed that mark, right? When is that? I mean, that's sometime in 2017, right? So we've already passed that. Okay. All right. So the last thing I wanted to talk about in this section is to tell you about something called logistic function. This is not something that you will be tested on. It is not something that you will be tested on, but it is something, it's a kind of a curve that you might come across in your careers as professionals, so you should know about it. That's why I'm bringing it up now, just so that you know what it is. That's all. You're not going to be tested on this. So a logistic function, I wanted you to know, because you know about linear functions, exponential functions, quadratic functions, square root functions, absolute value functions, right? We've covered all these functions in this course. But logistic functions is something that you might come across when you read a newspaper, when you read a paper or some kind of data, or in your professions, in the office environment, you might be handed a data that has that follows this kind of pattern, logistic function pattern. Not a linear pattern, not a quadratic pattern or absolute value or exponential pattern, but a logistic function pattern. A logistic function pattern is a function that has an exponential behavior, but it's not unlimited. It's not an unlimited exponential function behavior. It curves, it has a limiting, it has a ceiling to it. So up to a certain point, the quantity has exponential behavior, but then it gets limited. When it gets to a ceiling, there's a limiting factor here that will limit its rise beyond that limit. And that is a behavior. This behavior is a logistic function behavior, that one. See, that one, what you see on the left, that's exponential function behavior. It grows without bound, right? Do you see? It's going through, it grows without any limits. It just keeps growing. But logistic function, it has exponential behavior to a certain point, but then it curves back. It flattens. Now, in the age of coronavirus, I'm sure you've heard in the news that people and public health officials talk about flattening the curve. So that phenomena, people getting hospitalized, people getting sick, has a flattening trend to it once it peaks at some point. So it has an exponential pattern to some point, up to some point, and then it flattens out. It very much applies to the cases of coronavirus that were observed in New York and elsewhere before the new spike, right? Of course, after the businesses were open, then and after the number of tests went up, the number of cases that were reported to hospitals and emergency rooms and ICUs increased. But eventually it'll flatten out. Why is there flattening in this case? Well, because the virus, when it first gets introduced into a population, it's going to pick out all those that have compromised immune systems. So it's going to take, as it picks those individuals, it's going to have, it's right here, it's going to go through all those people, and it's going to infect them, and probably it's going to cause death to those people with compromised immune system. But at some point, the number of those people with compromised immune systems or pre-existing conditions, it will run out. So whether it's 10,000, 20,000, or 50,000, at some point, the virus will run out of such people in the population. So then it's still infecting people, but it's not killing people. It's not lethal to people, because people have better the remaining people have better immune system. Therefore, it'll flatten out. That behavior is the logistic function behavior. Okay? And it comes up, like I say, in the real world a lot. And I want you to know that. I think your book even mentions it. Okay, so that's, you see another logistic curve here. It goes up exponentially, then it flattens out. Okay, the other very common logistic data that has logistic function pattern is salary levels. If you take a job and stay in that job, say, for 40 years, your salary will increase up to a certain point. But it will flatten out, because for that position, that job, there's a certain limit beyond which the salary will not go up. So in other words, if you want to increase your salary, you either want to change your job to a job that has a higher overall salary, or you might want to take another second job. But staying in that job will not increase your salary beyond a certain limit. So salary over time does have logistic function behavior. At some point, it will no longer go up, it'll just flatten out. Okay? All right, having said that, we have come to the conclusion of another section, and I thank you for persisting through this video, for watching it, taking notes, and going through these exercises with me. And for now, have a nice day, and I'll see you again next time.